So on the GFAST, we're going to look at the single fiber solution, the CWDM and the DWDM options using SFPs and also using PON optics. So we start by, well, I guess we'll call this something, GFAST examples. Okay, so let's start with the GFL single fiber, no SFP, and of course that comes up with a 1490 downlink, and it happens to be a 1310 uplink. So again, we're doing point to point. We'll stick with our 80 kilometer link, and actually we're going to shorten that because the uplink optics we happen to know are limited by dispersion to approximately 30 kilometer optics. So we don't need quite so many field splices, and we have no amplifiers or splitters or anything at the receiver again, and we want to match up our devices. So we did this on the transmit. So this is our receiver, and you see that it has a -25, so we're transmitting at +3 from the head end, a very high power device, or a reasonably high power device, and a receiver of -25, so we have a 28 dB system gain, and we have lots of margin because we're only going 30 kilometers. So that makes good sense. Now we will look at the, and we'll come back to this in a little later, where we'll do some PON architecture where we put some splitters in here, and when you put the splitters in, of course you're going to start to get loss in the system, and then this margin will be eaten away. But for the moment, we will go to the GFAST with SFP optics, and so we will pick an SFP, and we'll pick a basic 28 dB one again, and we need to pick a wavelength, and of course SFPs do include the 1491, so in fact that wavelength works, but we'll just go straight to the 1491. We have our patch panel. We have no multiplexers because again we're doing a simple point-to-point link, and we'll change our fiber just for something to do. We'll go with our measured fiber over here. We'll stick with our 30 kilometers for the moment, and then we will go down and pick up a receiver, and the receiver needs to be with SFP optics, and of course now we need to pick an SFP, and we'll pick a 28 dB one, and we see we have lots and lots of margin. So just out of curiosity, how far would that go? And I think we know the answer is about 80 kilometers. Here we see we're down to about 2.3 dB of margin. You would probably look at that and go, well, it's a little bit weak. We'd rather use 5 dB, in which case we would go with an SFP with a 31 dB system margin. Is our recommendation when you do a new install. Is try to have 5 dB of margin if you can, and so there we have 5.3. So that would be a nice link. Now what we're going to do is we will go and look at our list of, we were going to do a DWDM, so let's just do that here. So what we will find this time is that the DWDM devices, because they're still running at 1 gigabit and they have very high system gains, that they will go an exceedingly long ways. Now that's the good news. The bad news is that they work in 1531, 1551, and 1571. You'll see that CDWDM, so that's dense WDM and coarse WDM for those frequencies. So we will pick the 1531, and we'll just have a look at that link, and we see that again it still has 5.3. Actually it's going to have more because we're going to pick a 36 dB DWDM SFP, and we have 4 dB of margin. So that's a healthy enough link that we would probably be okay with that. And if you needed longer, then you would pick a device with more margin here. Now what we'd like to do is go do a PON example. So this will be a GFL with a single fiber with no SFP, and it of course operates at the GFL single fiber transmit rate. And then the receiver is the GFN, but single fiber version. And we don't need an SFP in that case. And we have an incompatibility in our wavelength, and that would be GFL single fiber TX 1490 GLS, because we did the wrong receiver here. It should be the GFN single fiber. There we go. And we have about 2.3 dB of margin. Now, of course, as we mentioned earlier, that doesn't actually work that way because the uplink optics are not designed for that distance, because they're very wide lasers and have a lot of dispersion. And those items have not yet been built into the spreadsheet, but they will be over time. So now, just to refresh our memory, where we're going here is that we're leaving this world of point to point and going to the point to multipoint. And so what I've drawn here is a 8-way splitter here and a 4-way splitter here, and the GFL will support up to 32 GFN. So the OLT supports 32 ONUs. So what you might do when you first install a service, because your take-up rate is not that high yet, is that you might start with 8 or 16 customers per OLT, but you don't need to just have them all hanging off of this guy. So that if you had an area where you were expecting ultimately to have 32 customers, but initially you only had 4 or 5 or 6, what we would recommend is that you start with a 1 to 8 splitter here, and then we use a 1 to 4 splitter here, and this allows this OLT to be spread across all of this territory here. And this architecture will support 32 to 1 link budget loss. It will also support 32 devices. If you were installing a 100 megabit service, though, your normal ratio would be 8 of these to 1 of those. So if we set that as our target, 8 of these to 1 of those, then a field splitter at 8 is pretty good, because each one of these could go to its individual ONU or OLT. But in the beginning, we start with a 4 to 1 splitter in the head end and an 8 to 1 splitter in the field. So let's just have a look and see how that works on our link budget and how we implement that here. So what we will do is that this is a GFast PON with CO splitters. So we start with our head end. We have no SFP, single fiber, and now what we're going to do is we're going to put in our 4 to 1 splitter, which we saw in the other drawing, and we see that it comes up with about 7.5 dB loss. Then what we're going to do is we're going to go over our 30 kilometers of fiber, and the field splices and everything stay the same. And now we hit the field splitter, and that was an 8-way splitter. And we find that in this case we actually have almost 2 dB of loss. And so when you look at these access systems using PON, they're really designed, when you're going to use a 32 to 1 split, to run about 20 kilometers or so. And you can see that here, that we have not a whole heck of a lot of margin, although typically you don't actually have a receive patch panel in a consumer system. You'll just run the fiber to the house, and if you have to monitor it, you will be running it there. So we can see here that a 32 to 1, 20 kilometers is the max, and we would probably run it more like 15. So let's just assume that this is an access network, and which is what PON is designed for, and this was your initial implementation. So we find that this will work, and like I said, maybe initially the link is a little weak, but as you add customers, what we're going to do is we're going to remove that splitter there. And then you'll find that the link gets a little stronger as time passes, because you've got fewer splitting of the power. So here we've got our 8-way splitter here, And so we look at how does this link perform at the end of time. Well, that splitter comes out. We increase, of course, the number of OLTs, and we find that in this case now we have, in the fullness of time, we have way more margin than we actually need. So now what we're going to do is we're going to look at the a GFast CWDM example. So in that kind of system, the head end is typically a SFP optics device. Actually, why don't we start with the VFast CWDM. It has no SFP, and it operates at any one of the standard frequencies. We'll pick 1511 for something to do, and then what we're going to do is we're going to put in a 8-channel CWDM multiplexer. So just to refresh your memory as to what we're looking at here, we have an 8-channel multiplexer. There's actually a pair of them, one for this way, one for that way, one for east, one for west. So you use these devices in pairs at each end. And in this case I'm showing a GFast implementation, but it's the same architecture for the VFast CWDM. So we put in our multiplexer, and we're going to go probably a whole lot longer. So let's put in a 60 kilometer link. We'll keep going with our measured fiber here, or maybe not. Maybe we'll go with generic 652B because we've put some allowance in for field splices here. And there's no splitter in this case, but there is a multiplexer at the other end, another 8-channel CWDM multiplexer. So we've got loss on the transmit side, loss on the receive side, and now we're going to have to pick off the right device, the CWDM device, and it has just tons and tons of margin as well, because there's not really a whole lot of loss and in that multiplexer. So we could go with maybe an 80 kilometer link and you'd still look really good. So let's say we decide that, well, you know what, we're a little unsure about the future here. Let's see if this thing will support a 16-channel multiplexer. And of course, as you would expect, nothing is free in the world of engineering. You get more loss from your 16-channel, and lo and behold, with a nice new shiny fiber, life is pretty good. You've got lots of margin here, a full 5 dB. So that's pretty good. Now if you went to a new installation, I see in this case it's the same, so that's not going to matter. If you went to our splice field example, we have a little bit more loss there, but of course we have no field splices. And we find there that our margin, it's 2.5 dB. So it's okay, but it's not great. But so again, a very robust link using the 8 and the 16-channel CWDM multiplexers. So that's quite encouraging. Now we'll look at what happens when we want to upgrade to gigabit. So we go to head-end device with some SFPs, and we'll start with the 28 dB SFP. And we will interface to the mating device at the far end, that's the GFN. And we have to put in an SFP, and we'll put in an SFP value. And we find that there's not really a whole lot of margin there. So when we go with the 16-channel multiplexers and you want to do an 80 kilometer link, we probably are going to have to use a little bit better device. So we'll increase our system margin by 3, and now we're up to 3.5 dB. And if you're comfortable with that, that's good. If this is a new system and you're installing new fiber, of course you would expect to get better results because you'd use something like that. And we have to make some allowance for field splices, and we find that we actually have over 5 dB. So this architecture with the CWDM and the 8 or 16-channel mux looks like it'll go a good long ways. So that concludes that set of examples, and the next thing we're going to do is look at adding DWDM to our CWDM system.